Hi guys, welcome to my video. Today we are going to discuss about heap trees and priority queues in very simple and super easy to understand way. This is very important in data structures because this is used by tons of applications in real world. So let's dive in. In this video, we will learn what is a priority queue, what is a heap tree, how a heap implements a priority queue, NQ and DQ operations, a simple example to understand how priorities work. Let's get it started. What is a priority queue? Here you can see normal queue and priority queue. First, let us understand what a priority queue is. A priority queue is a special type of queue where each element has a priority. In a normal queue, the first element that comes in is the first to go out. We called it FIFO. But in a priority queue, the element with the highest priority is removed first. If two elements have the same priority, then they are served based on their order of insertion. Let's take an example. Think about a hospital emergency room. A patient with a serious condition is treated first, even if they arrive later. This is how a priority queue works. Then, what is a heap tree? Now, let us talk about heap trees. A heap is a complete binary tree that follows a special rule called heap priority. First of all, we should talk about binary tree data structure. A binary tree is a tree data structure where each node has at most two children. That's why we are called it binary tree. It can be unbalanced or incomplete. But a binary heap is a complete binary tree, which means all levels fully filled except possibly that last, which is filled left to right. A binary heap also should satisfy the heap property. There are two types of heaps. In max heap, the parent node is always greater than or equal to its child nodes. The largest element is at the root. Then min heap, the parent node is always smaller than or equal to its child nodes. The smallest element is at the root. Heaps are usually stored using arrays, not pointers. First, we store the root node at the 0th index of the array. Then we add its left child followed by its right child and continue in the manner level by level from left to right. This layout allows us to access any parent or child node using simple index calculations. Now let's look at the formulas for finding the parent and children of any element given its index in the array. For example, consider an element with the value 30 at index 2. To find its left child, we plug I equals 2 into the left child formula, which gives us index 5. So index 5 is the left child of the element at index 2. Similarly, using the right child formula with I equals 2, we can find the right child index to locate the parent of the current node. We use the parent formula with I equals to and take the flow of the result to determine its parent index. This simple indexing allows efficient traversal up and down the heap. Now let's take a look at how insertion works in a max heap. Suppose we want to insert a value 43 into our max heap. To do this, we first append 43 to the end of the array, which is equivalent to placing it in the next available leaf node in the complete binary tree structure. Now the newly inserted element might be violating the max heap property. To fix this, we check if the element is greater than its parents. If it is, we swap them to restore the heap structure, effectively bubbling up the element. We continue this process comparing and swapping the each successive parent until heap property is restored or the element reaches the root. Keep in mind the tree structure we visualize is just to help us understand the relationship between elements. In reality, all heap operations happen directly within the array. Let's talk about how heap implements a priority queue. Now, how does a heap implement a priority queue? In a priority queue, we always want fast access to the highest or lowest priority element. A heap helps us do this efficiently. So, how it works? In a max heap, the element with the highest priority is always at the root. In a min heap, the element with the lowest priority is always at the root. Because of this property, insertion, that means NQ, is very efficient. Deletion, that means DQ, is also efficient. That is why heaps are commonly used to implement priority queues. Let us see how NQ works in a heap. Insert the new element at the end of the heap. Compare it with its parent. If it violates the heap property, sweep it with the parent. Repeat this process until the heap property is restored. This process is called heapify up. Let's talk about time complexity. NQ takes NQ operation takes O log n time. In a priority queue, DQ means removing the element with the highest priority. So to do that, first remove the root element. Second, replace the root with the last element in the heap. Compare the new root with its children. Swap it with the appropriate child to restore heap property. This process is called heapify down. Time complexity. DQ operation also takes O log n time. Example. How priority determines order. Let us understand this with a simple example. Assume we have a max heap priority queue. We insert the following elements with priorities A, B, C, D. After inserting, elements B will be at the root because it was the highest priority. The DQ order is B, D, A, C. So, even if an element is inserted later, higher priority elements are always served first. First, we create a class called minHeap. Inside it, we have an integer array called heap to store elements, a variable size to track how many elements are inside the heap, and capacity to define maximum size of the heap. In the constructor, we initialize the heap with a fixed capacity. We also set the initial size to 0 because the heap starts empty. First, we create a class called minHeap. Inside it, we have an integer array called heap to store elements, a variable size to track how many elements are inside the heap, and capacity to define maximum size of the heap. We also have a swap method. This simply swaps two elements inside the array, which is very important when maintaining heap order. Now let's talk about NQ, which means inserting an element into the heap. First, we check if the heap is full. If there's space, we add the new value at the end of the array. Then we perform heapify up, also called bubble up. During heapify up, We compare the inserted element with its parent. If the child is smaller than parent, we swap them. This continues until the heap property is restored or we reach the root. Next is dequeue, which removes the minimum element, meaning the root. Here's how it works. If the heap is empty, we return -1. Otherwise, we store the root value. Move the last element in the heap to the root. Reduce the size. Call heapify to restore the min heap property. Finally, we return the removed root value. The heapify method is used after deleting an element. It compares the current node with its left and right children, then finds the smallest among them. If the smallest is not in the current node, we swap. Then we recursively call heapify on the new position. This pushes the element down to the tree until the heap property is restored. In the main method, we can test our min heap. Applications of priority queue using heap. In the summary, we can say a priority queue processes elements based on priority. A heap tree is an efficient way to implement a priority queue. NQ and DQ operation takes O log n time. Heaps ensure that the highest or lowest priority element is always available.
Thanks so much for the watching. I really hope this cleared things up for you on heaps and priority queues. So if you enjoyed the video, please give it a like and hit the subscribe and bell button for more data structures videos.